Hello everyone, welcome back to my YouTube channel where I'm going to be bringing you through this failure problem today. So basically this failure problem is where we have to consider a state of plane stress in a structural component represented by the stress element provided below, where sigma x is yet unknown and tau xy. So the shear stress in the x on the x-plane in the y direction is 50 kivs per square inch. So suppose that the structural component is made of a ductile material with a yield strength of 200 ksi. Using the maximum shear stress theory, we want to determine the maximum value of sigma x for which the ductile material and the structural component does not fail. Part B is for the maximum value of sigma x found above, thus maximum distortional energy theory predicts failure of the material. And B is suppose now that the structural component is instead made of a brittle material with equal ultimate strength and tension and compression of sigma uh, of ultimate stress tensile equals ultimate stress compressive equals 200 ksi. Using Mohr's failure criteria, determine the maximum value of sigma x for which the brittle material and the structural component does not fail. So to review, the maximum shear stress theory and maximum distortional energy theory are both theories which apply to ductile materials, while the Mohr's failure criteria is a um, failure theory that applies to brittle materials. Um, a a member under tensile loading, if it is a ductile material, tends to fail due to shear stress, due to this axial pulling, this axial force applied at a 45-degree angle due to shear stress. And this is the basis for our maximum shear stress theory and maximum distortion energy theory. So the maximum shear stress theory shows that ductile materials are more likely to fail from shear than from a kind of distortion. Um, and first, we are going to draw the very useful graph that we can use to predict failure for the maximum shear stress theory and maximum distortional energy theory. And it looks something like this. So, for the maximum shear stress theory, we have this sort of diamond-looking graph. And for our maximum distortional energy theory, we have kind of an ellipse that encompasses uh every single point of this maximum shear stress theory. Yeah, it's supposed to be a smoother ellipse. Like this part, these parts are supposed to be smoother. But anyways, and this is a graph of principal stress 2 versus principal stress 1. And at these points where the diamond and the ellipse intersect each other, it's to say that the yield stress values of both theories are predicted to be the same value. So the the value at which the yield stress occurs is predicted to be the same regardless of whether we use the maximum shear stress theory or maximum distortional energy theory. However, on these other points, the theory for the maximum shear stress theory predicts a lower value than the maximum distortional energy theory, and thus the maximum shear stress theory, denoted commonly by MSS, is more conservative. More conservative. So the values at each of these points are yield stress, yield stress indicating that the yield stress predicted by both theories are the same. Over here we have 0 and then yield stress. And over here we have negative yield stress 0. And over here we have negative yield stress, negative yield stress. Over here we have 0, negative yield stress. And over here finally we have yield stress 0. So for the maximum shear stress theory, um the value for the yield stress is equal to 2 times the absolute maximum shear stress, or equivalently the absolute maximum shear stress is equal to the yield stress over 2. So thus we can write over here yield stress is equal to T max absolute uh times 2. What about for the maximum distortional energy theory, which we will call MDE? Well, for that energy theory, we can introduce what we call a von Mises stress, which is different than the yield stress. And the maximum distortional energy failure criterion says that if the von Mises stress calculated from the principal components of plane stress exceeds the yield strength of the material, failure of the material is predicted. Whereas for the maximum shear stress theory, we have that the yield stress cannot exceed 2 times the absolute maximum shear stress. So according to the maximum shear stress theory, a ductile material in a general state of stress will fail when the shear stress reaches the same value as the shear stress when it fails under a uniaxial test. That is when T max absolute is equal to sigma y over 2. That's it, nothing else. Failure analysis for plane stress using the maximum shear stress theory consists of calculating the absolute maximum shear from a known state of stress. The maximum distortional energy failure theory for ductile materials says that the yield strength is equal to the von Mises stress, and the von Mises stress can be calculated by the square root of principal stress 1 squared plus principal stress 1 times principal stress 2 plus principal stress 2 squared. Thus, we can you apply these to our problem. So we can write that down here. MDE says that the yield strength is equal to the von Mises stress, and the von Mises stress is equal to principal stress 1 squared minus principal stress 1 principal stress 2 plus principal stress 2 squared. Well, this will come in handy. For part B, we have to come consider how brittle materials fail. So brittle materials fail suddenly by fracture without prior yielding. Experiments have shown that the value of the normal stress on the failure plane for a biaxial general state of stress is not significantly different from the fracture stress, sigma sub u, in a uniaxial stress test. So, since brittle materials simply fail without prior yielding, instead of sigma y, we will have sigma u. So instead of yield stress, we will have ultimate stress used in the failure theory for brittle materials. For the failure theories for brittle materials, there are also two different divisions. One is the failure theory for brittle materials, the maximum normal stress. Max normal stress. So for this one, the motivation is that brittle materials fail suddenly by fracture without prior yielding. And experiments have shown that the value of the normal stress on the failure plane for biaxial general state of stress is not significantly different from the fracture stress, sigma u, in a uniaxial stress test. Um, so the maximum normal stress failure criterion, max normal stress criterion. Include that the fracture of a brittle material occurs when the maximum principal stress equals or exceeds the ultimate normal stress when the same material fractures in a uniaxial test. Note that this criterion assumes that compressive failure occurs at the same ultimate stress value as do tension failures. And in terms of principal stresses, the failure boundary for a brittle material by the maximum normal stress failure criterion is defined as the absolute value of principal stress 1 is equal to sigma u, or the absolute value of the principal stress 2 is equal to sigma u. Um, oh wait, and the u should be capitalized because it represents the ultimate stress. So yeah, should probably put u here and u there. So the general state of plane stress. So graphically, we can represent this as follows. Drawing our Cartesian coordinates. So I'm gonna move it down a little bit. We have principal stress 2, 1, and sigma P2, sigma P1. So we have four corners, and this is to kind of graph this whole idea over here. At the far upper right corner, we have sigma u, uh, u, ultimate stress. And over here we have ultimate stress, negative ultimate stress. Over here we have negative sigma u, negative sigma u. And here we have negative sigma u, sigma u. All right. So this is the general state of stress, general state of plane stress. But however, we have another failure theory for brittle materials, and that is the Morse criterion, because many brittle materials have a lower ultimate strength in tension, sigma ut, than in compression, sigma uc. That is that sigma ut is less than sigma uc. This is kind of analogous analogous to what we found in the criteria um for materials that fail due to shear stress where one is less than the other. So for Mohr's criterion, we have when principal stress 1 and principal stress 2 have the same sign, failure occurs if either of the following stress limits is reached. If either sigma max equals sigma sigma sub tu, that means ultimate stress and tension, or sigma minimum is equal to negative sigma sub cu in compression. When sigma, when principal stress 1 and principal stress 2 have opposite signs, Mohr's failure criterion states that failure occurs when the principal stress 1 over sigma, the ultimate stress and tension is equal to the principal stress 2 over ultimate stress and compression, all of that plus 1. The above combination constitutes Mohr's failure criterion. And graphically, we can basically represent it as such. So we can represent it as, and this is Mohr's criterion. Oops, okay. That's supposed to be a square, and this is supposed to be a larger square, and connect the 2 points. And this is supposed to be a symmetric figure, but oh well. But anyways, the points of the vertices, oh wait. So this point over here is sigma ut, comma, sigma ut, and uh, this point over here is oops, is sigma ut, comma 0, and this part over here is negative sigma ut, comma negative sigma uc. Oh, sorry, this is supposed to be uc. And this point over here is negative sigma uc, comma 0. So Moore's failure theory for brittle materials is also summarized over here. If sigma P1 and sigma P2 are of the same sign, sigma P1 equals sigma Tu, or sigma P2 equals negative sigma Cu. If sigma P1 and sigma P2 are of different signs, sigma P1 over sigma Tu equals sigma P2 over sigma Cu plus 1. Okay, so from what we previously found, for part A, we want to use the maximum shear stress theory to determine the maximum value of sigma x for which the ductile material and the structural component does not fail. And to do this, we would first have to find our values for sigma average and principal stress 1 and principal stress 2 and our R value. So we are going to work it over here. So we know that sigma average is equal to sigma x plus sigma y over 2. But since sigma y over here is 0, since there's no vertical component over here and here, sigma y is equal to 0, so this is simply equal to sigma x over 2. And now we know sigma average, so we want to find the R value. The R value will give us the radius of our Mohr circle. So R value is sigma x minus sigma y all over 2 altogether squared plus tau xy, which is the shear stress value, squared. So here our R value is going to be square root of remember that sigma y is 0, so we will get sigma x over 2 altogether squared plus, and there is a tau xy value, so we will use tau xy squared as our value here. Now our principal stress 1 is going to be a sigma average plus R, which we can write simply as, since R is such a long equation, sigma x over 2 plus R. And we intuitively know that we just plug this equation in here. And principal stress 2 is equal to sigma average minus R equals to sigma x over 2 minus R. Now what we want to do to plot our Mohr circle, since we're not explicitly given values for sigma x and tau xy here, is to compare the relative magnitudes of R and sigma average. So for instance, on our Mohr circle, which is a graph of sigma versus tau, we are going to have sigma average be, well, we know that sigma x is positive and sigma x over 2 will thus be positive too and be somewhere over here. And our R value, which is sigma x over 2 squared plus tau xy squared, and the square root of that is going to be greater actually than sigma average. Since sigma average is simply sigma x over 2, while this R radius term has an additional term of tau xy. So we know that the radius is going to, for principal stress 1, is going to lie to the right of the sigma average value, which is going to be principal stress 1. And then what about principal stress 2 is going to lie to the left of our sigma average over here. And now we have our Mohr circle. And we want to find the maximum value of sigma x, for which it does not fail. So we have our in-plane Mohr circle over here. Let's see if I can draw a nice circle. I think that's pretty good. And for that, remember from our formula that from this formula over here, that we need to find the absolute maximum shear stress, which is different than the in-plane maximum shear stress. The in-plane maximum shear stress is always given by R, but our maximum absolute shear stress is not always equal to R. It might not be equal to R, and it's found from drawing our outer plane Mohr circle, which is basically kind of tangent to our inner plane Mohr circle here. I guess that kind of looks like a circle, but for our outer plane Mohr circle, how do we know it looks something like this? Because remember that our values for sigma 1 has always to be greater than sigma 2, has always to be greater than sigma 3. So sigma 3 is always equal to 0 in our 2D problem over here, because this is a two-dimensional problem. So sigma 3 will just be equal to 0. So now we have these values over here. Um, we Now we have these values over here. We can find which one is our sigma 1 and sigma 2 and sigma 3. So sigma 1 is going to be our maximum value for normal stress, which is going to be principal stress 1, since sigma x over 2 plus r is greater than sigma x over 2 minus r is greater than 0. So principal stress 1 is going to be our sigma 1 because it's greater than principal stress 2, which is greater than 0. Um, and thus our absolute maximum shear stress, which is always given by um, the largest shear stress, no, the largest stress minus the smallest stress over 2 is going to be principal stress 1 minus 0 over 2, which is equal to principal stress 1 over 2. Wait, hold on. Actually, let's backtrack over here. I think I made a mistake somewhere over here. So I graphed the in-plane Mohr circle wrong, which resulted in me graphing the outer plane Mohr circle wrong. So let's redo that part. Um, so actually, since the magnitude of R is greater than our sigma average, our principal stress 2, the sigma average minus R is going to be a negative value. Um, so principal stress 1 and principal stress 2 will have opposite signs. So it's very important to watch out for that. Principal stress 2 will, so let's draw sigma average as somewhere over here since we know it's positive. And then principal stress 2 over here and principal stress 1 over here. So now our outer plane Mohr circle will look something different. Um, since our outer plane Mohr circle says that sigma 3 is always equal to 0. And now over here, since sigma 3 is always equal to 0, we will actually have sigma 1 greater than sigma 3 is greater than sigma 2. So our sigma 3 is equal to 0. And how our outer plane Mohr circle will look like, this time we will have two different circles like that. And okay, this one also implies that um, principal stress 1 is greater than 0 is greater than principal stress 2. And this Tmax absolute will be uh, the largest value minus the smallest value, which in this case isn't going to be sigma 3 anymore. It's going to be sigma 2. So it'll be still principal stress 1 minus okay, it won't, this value will also change. So many things will change, so just be careful about that part. So plugging in known values, we have that sigma 1 is equal to principal stress 1, which is equal to sigma x over 2 plus r. And then we have minus sigma 2, which is over here principal stress 2, which is minus sigma x over 2 minus r. So, and then all this is over 2. So our sigma x over 2 values cancel out. And we are left with r minus r, which is 2r over 2, which is equal to r. So our Tmax absolute is equal to r. And if we review again our maximum shear stress theory, it says that Tmax absolute is equal to the yield strength over 2. Um, So so back over here, since T max absolute is equal to uh the yield strength over 2, we'll have the R equals the yield strength over 2. So the yield strength will thus be equal to 2R. However, we are not done yet since we were asked to find the maximum value of sigma x for which it does not fail. So that would not be equal to our yield strength. We will have to plug in our value for R, which over here is sigma y equals 2 times, what was our value for R? It was the square root of sigma x over 2 altogether squared plus tau xy squared. And let's see if we're given some known values. Oh yes, we are. So we are given that the yield strength is 200 KSI. So let's go ahead and plug that in. 200 is equal to 2 square root of sigma x squared over 4 plus, and what is the tau xy value? The tau xy value is equal to 50 KSI. So we're given no values, but it's better to plug everything in afterwards. So solving for sigma x, we get that sigma x is is equal to 173.2 KSI. So that is our answer for part A of our question. So for part B of question A, we want to find for the maximum value of a sigma x found above, does the maximum distortional energy theory predict failure of the material? So I think it will be helpful to calculate our principal stresses in this question. So we know that oh wait, sigma x is yet unknown. Okay. And what about tau xy? Tau xy is 50 KSI. So we get that principal stress 1 is equal to sigma average, which is sigma x over 2, plus our R value, which is square root of sigma x over 2 squared plus tau xy. And our goal here is to find our sigma principal stress of 1 to see where it lies on this maximum shear stress theory and maximum distortional theory graph, because the maximum shear stress theory is this figure, the diamond represented by the diamond, and the maximum distortional theory is represented by the ellipse. So by determining where sigma P1 lies over here, we can drop down and see whether MSS theory is going to predict less because it's more conservative, or maximum distortional theory is going to predict less. Or maximum distortional theory will never predict less. It will only predict either greater than or equal to the strength predicted by the maximum shear stress theory. Because at these specific points, the yield strength predicted by both theories are the same, but most everywhere else, the MSS theory predicts a lesser value because MSS is more conservative. So plugging in our value for sigma x and our value for tau xy, which was, I believe, 50 ksi. Okay, so 50 ksi, we get using 173. Point two. Sorry, my tablet is acting up. So calculating our values for principal stress 1 and principal stress 2, we see that the coordinate on the MSS graph, the maximum shear stress graph, is going to be given by 186.60, comma, negative 13.40 in KSI. So let's put KSI. And we see that since we know that our yield strength is 200, um, it's going to be at these values are going to be 200 in magnitude. So we know that principal stress 1 lies a little bit to the left of the 200 since principal stress 1 is 186, which is slightly less than 200. And this checks out because for that value, we have a small value for principal stress 2, which is negative 13.40. And this very small distance over here is close to 13.40. So we see that over here, although the it lies on the diamond graph, the maximum shear stress graph over here, it does not lie on this outer circle over here. So only the MSS theory, the maximum shear stress theory, predicts failure. So let's get a closer look at this. So just make sure you guys understand. This value is 200. This value is slightly less than 200, which is about like 180, as we found uh, sigma principal 1 to be. And then this value, which is sigma principal 2, is going to be about 13, which checks out. But it only lies on the graph of the MSS theory curve, but not on the graph of the maximum distortional energy theory curve, which if it were to lie on that would lie over here. So our correct answer for part B is no, MSS is more conservative, so only MSS predicts failure, but not the maximum distortional energy theorem. Okay, so now we can move on to part B, which says that suppose now that the structural component is instead made of a brittle material with equal ultimate strengths in tension and compression of sigma ultimate tensile is equal to the ultimate strength in compression of 200 ksi. Using Mohr's failure criteria, determine the maximum value of sigma x for which the brittle material and the structural component does not fail. So we can review our theories over here, and some of it is cut off, so I'm going to zoom out. So as you mentioned before, contrary to the max normal stress criterion over here, the Morse criterion is a little different because many because while the maximum normal stress criterion assumes that compressive failure occurs at the same ultimate stress value as do tension failures, Morse criterion takes into account that many brittle materials have a lower ultimate strength in tension or sigma UT than in compression, sigma UC. So in this case, the maximum normal stress criterion cannot be used. So if we review our theories, we see that Mohr's failure theory for brittle materials states that if sigma P1 and sigma P2 are of the same sign, we get that sigma P1 is equal to sigma TU, or sigma P2 is equal to negative sigma CU. And if sigma P1 and sigma P2 are of different signs, we get that sigma P1 over sigma TU is equal to sigma P2 over sigma Cu plus 1. So since we found that principal stress 1 and principal stress 2 are of opposite signs, and we don't even need to solve for principal stress 1 and 2, we can just see from our value of R, since our value of R is greater than sigma average, principal stress 1 and 2 are going to be opposite signs. That's why like one of them is on the negative sigma axis and the other one is on the positive sigma axis. So because of that, we're going to use the second formula we saw here. So we're going to use that sigma P1 over sigma TU is equal to sigma P2 over sigma CU plus 1. And here again, we want to determine the maximum value of x. So we can't use our value of sigma x over here. We're actually solving for it. So we're going to have to go back to our relations for sigma P1 related to x and r. So it's going to be sigma x over 2 plus r over sigma tu, which we can plug in right now. Sigma tu is equal to sigma uc is equal to 200 ksi. So over 200 is equal to sigma x over 2 minus r over 200 plus 1. And our value of r, I believe we solved for it earlier. Or no, we cannot solve for it yet. R is going to be the square root of sigma x over 2 squared. And then we can go ahead and plug in tau xy as 50 because that was one of the givens if we go back to our criteria. So tau xy equals 50 ksi. Um, and to solve this equation, we have to isolate the sigma x on one side. So we can do sigma x over 400 minus sigma x over 400 um plus r over 200 plus r over 200 is equal to 1. And note that certain things cancel out nicely. These two cancel out, and r plus r over 200 is 2r over 200, which is simply r over 100. So r over 100 equals 1, which implies that r is equal to 100. And now we can plug in our value for r, which is square root of sigma x over 2 squared plus 50 squared. And squaring both sides, we get that 100 squared is equal to sigma x over 2 squared plus 50 squared. Solving for sigma x, we get that sigma x is equal to 173.2 KSI. So we have now gone through all parts of our problem, and I hope this problem was useful to you. And thank you guys so much for watching. And if you have any questions or concerns, leave them in the comments and I'll be sure to respond to them. And don't forget to like and subscribe if you haven't already for more updates in the future. Thank you. Bye.